Hey, my Math 254 friends. Welcome to your lecture on Rolle's Theorem. This is the first part of section 4.2. 4.2 is entitled the mean value theorem. Rolle's theorem is a specific case of the mean value theorem. We'll see that in part 2 of this lecture. But right now we're just going to keep it here and discuss Rolle's. So Rolle's theorem says if you have a function that behaves nicely on a closed interval or on an interval, that is, it's continuous on the closed interval, so it's continuous between a and b and at the endpoints, and it's differentiable everywhere in the interval between a and b. And the third condition that needs to be satisfied is the output at the endpoints is the same. The function value at a is equal to the function value at b. If this happens, then we can conclude that somewhere between a and b, there's a value c where the derivative is 0. Let's take a look at what this means visually. So if you want to take a minute and pause this and write that in your notes, that would be great. So what Rolle's theorem is telling us is that if we have a function defined on an interval from a to b, it has to be behave nicely between a and b. It has to be continuous, so there's no holes, breaks, or jumps. It has to be differentiable, so there's no vertical tangents or peaks. And the output at the endpoints is the same. So wherever the output at A is, must be the same as the output at B. So now what's going on between these 2 points? Draw any continuous, nice continuous function you want. Continuous and differentiable, so a function behaves nicely between those 2 points. So you can either draw my function, you can draw your own function, but in either case, if you start at A and you walk along the curve, somewhere between A and B, the derivative is going to be 0, or the tangent is going to be horizontal. So you see in my case right here, that's going to happen at the top of this hill. So as long as you draw a function that satisfies all 3 conditions, it's continuous from A to B, differentiable between A and B, and the output at the endpoints is the same, you're going to be able to find a value c where your tangent is horizontal. So that's Rolle's theorem for us. So let's apply this to an example. Let's suppose we were given the function x squared minus 3x plus 2 on the interval from 1 to 2. We want to verify the hypotheses of Rolle's theorem are satisfied, and once we do that, we can find the values of c that satisfy the conclusion. All right, so the first 2 hypotheses of Rolle's theorem state that this function has to be continuous and differentiable on this interval. Well, polynomials are continuous and differentiable everywhere, so we can just simply state that f of x is a polynomial, and polynomials are continuous and differentiable everywhere. Polynomials behave very nicely. So without much ado, 1 and 2 are satisfied. All right, to show 3, in order to show 3 is satisfied, we must show the output at the endpoints is the same. So we want to find the value of f of 1. We want to find the value of the function at 2. So we're going to plug 1 back into my original function. We plug 1 in, we get 1 squared, 1 minus 3 times 1, which is 3. 1 minus 3 is negative 2, plus 2 is 0. So the output at 1 is 0. The output at 2 is, well, 2 squared is 4, minus 3 times 2 is 6, negative 2 plus 2 is 0. So these are the same. So therefore, 3 is satisfied. So Rolle's theorem guarantees us there's a number between 1 and 2 where the derivative of this function equals 0. So to find that value, we're going to take the derivative, 2x minus 3, and we're going to set it equal to 0. And you'll be guaranteed to get a number between 1 and 2. So we're going to add 3, divide by 2, and we get 3 halves. 3 halves is 1.5, which is between 1 and 2. So as expected, we found the value of c. We just call it c. You can just say x equals 3 halves. That's sufficient. But c is the value in the conclusion Rolle's theorem. 3 is the number between 1 and 2 whose derivative is 0 for the function x squared minus 3x plus 2. So just to give you a little visual, if we graph this guy, which I already did, x squared minus 3x plus 2, and I graph it. So there it is from our regular 10 to 10 viewing rectangle. Where I'm looking at is only between 1 and 2. So I'm going to change this to, I'm only going to go from 1 to 2. When I graph it again, it's not going to be very much going on here. So I'm going to change my y scale so I can get more of an idea. I'm just going to do that. I think this will give me a good picture. So here's this function. This is the output 0 at 1. Here's the output 0 at 2. And between 1 and 2, right here, the derivative is 0, and that's going to occur at the point 3/2. All right, so let's try it with a little bit more complicated of an example. First, we have to determine if Rolle's theorem can be applied. If so, then we're going to find all values of c that satisfy the condition that the derivative equals 0 between 0 and 2. So here, whoops, I didn't write my function. Let's write my function because that would be helpful. For the function f of x equals e to the x squared minus 2x. All right, so what we have going on here, we have an exponential function. And we have a polynomial. We know polynomials behave nicely on any interval, so we know that this is continuous and differentiable on 0 to 2. But likewise, if you go back and revisit our sections on continuity and differentiability, e to the x is continuous and differentiable. So seeing these are both continuous and differentiable, the product of continuous and differentiable functions is also continuous and differentiable. So both continuous and differentiable everywhere. So their product is continuous and differentiable. So 1 and 2 are satisfied. So now let's check condition 3. We have to check the output at the endpoints. So we're going to plug in 0 and get our value. We're going to plug in 2 and get our value. So our output at 0 would be e to the 0 times 0 squared minus 2 times 0. Well, e to the 0 is 1, but 0 squared minus 2 times 0 is just 0. So we're back at 0. Just a coincidence that both of these have outputs of 0. I meant this in the previous example. At 2, we're at e squared, 2 squared minus 2 times 2, and that also equals 0 because this is 4 minus 4 inside there. So these are the same. They don't have to both equal 0. Again, that's just a coincidence. I could put plus 6 on the end here, and we would get each of them have an output of 6. So 3 is satisfied. So the output at the endpoints has to be the same. It doesn't have to be 0, but it does have to be the same. So now, by Rolle's theorem, we are guaranteed that there is a number between 0 and 2 where the derivative is equal to 0. So what we're going to do is now we're going to take the derivative. So I'm going to rewrite the function here. E to the x squared minus 2x. We're going to take the derivative. We have a product, so we have to use the product rule. Derivative of the first times the second plus the first times the derivative of the second. 2x minus 2. I'm going to factor out the e to the x. If I factor e to the x out of here, we're left with the x squared minus 2x from this piece. Plus, and I took the e to the x, brought that out front. We're at 2x minus 2. So we're going to clean that up a little bit. We get e to the x squared minus 2 because these two guys cancel out. And we're going to set that equal to 0. So we're guaranteed somewhere between 0 and 2. E to the x times x squared minus 2 equals 0. Well, here we have a product. We use the zero product principle. So either e to the x equals 0, right, or x squared minus 2 equals 0. Well, e to the x here has no solution. E to the x never equals 0. It falls completely above the x-axis. Here we solve for x equals 2. We square root both sides. We get x equals plus or minus the square root of 2. Don't forget the plus or the minus. So x is either going to equal negative square root of 2 or the positive square root of 2. Now what's really important, especially when you're putting your answers into your XYZ homework, remember we're looking, our interval of interest is just 0 to 2. So square root of 2, which is less than 2, falls between 0 to 2, but negative square root of 2 does not. Negative square root of 2 still causes the derivative to be 0. It's just not in our interval of interest. So therefore, my only answer, the value of C, Rolle's theorem was looking for here, was the square root of 2. So let's see if I can take a minute and get this into our calculator. I'm going to plug in the original function y equals e to the x. Let's clear that in a second. Sorry, I can't see. I didn't grab my glasses. And then we're going to do x squared minus 2x. I'm going to close, and I'm going to go to Zoom Standard. Do my standard viewing rectangle. Not sure what information this is going to give us. Woo, look at that. All right, so now let's go. I'm going to do my window. I'm going to only look at this between 0 and 2 because that's what our interval of interest. So 0, it goes down, and right there. So at the output, at both endpoints is the same. And right here, it's going to reach. It's a place where the derivative is equal to 0. And that x coordinate right there is going to be the square root of 2. All right, friends, ending this one here so it downloads quicker. We will pick up in a few minutes with the mean value theorem.